And now, to kick things off, I'd like to introduce our first keynote of the day, titled Towards 6G Wireless Communication Networks Vision, Enabling Technologies and New Paradigm Shifts. Now, fifth generation wireless communication networks are being deployed worldwide, and more capabilities are in the process of being standardized, such as massive connectivity, ultra reliability, and low latency. This talk will review recent advances and future trends, and to bring us through all of this is a Michael Henry Strater University professor at Princeton University, with recent recognition of his work, including the 2017 IEEE Alexander Graham Medal and honorary doctorates from several universities in Asia, Europe, and North America. Ladies and gentlemen, let's welcome Professor Vincent Poor.
Thank you very much, and good morning, everyone. Very pleased to be here to speak to you this morning. Let me see if I can share my screen. I need permission to share my screen, actually. So I see that the host has disabled that, but it would be nice to be able to share my slides. So
yes, we have just put that function on, so you should be able to see your slides.
Yep. Thank you. Okay, good. There we are. I hope you can all see my screen now.
Yes, okay, we can see your screen perfectly.
So thank you very much for that kind introduction, and good morning, everyone. It's nighttime in the East Coast of the United States, but I know it's morning there. And I'm very happy to have this opportunity to speak with you today. I'm going to apologize in advance for my voice. I have a bit of laryngitis this evening, but I think I'll be able to get through my talk without much trouble. So as was said, we are currently deploying 5G, and of course there are still many things to be done to bring 5G to its potential. But today I want to talk about 6G, and of course this is we're thinking ahead almost a decade when we start thinking about the next generation of wireless. I know yesterday some of the talks also touched on some aspects of 6G, and there will be some repeat of some of the things that you learned yesterday, but I hope I can put it all in perspective in a different way. What I'm going to talk about today was published in a paper in Science China in January earlier this year. And that paper, and I'll just show you on the next screen, that paper had a large number of authors. So what I'm going to talk about today is really a consensus of many different perspectives about 6G. And I would encourage you, if you are interested, to take a look at this paper, because it goes into a great deal of depth on some of the things I'm going to just touch on today. Also, I'll just point out that there are many people here, I'm sure many familiar names to many of you here on this author list. All of them have their own inputs to this, and they're experts in many different aspects of wireless. I'm only an expert in some of the areas, so I'm going to touch on a lot of things, some of which I'm really not expert on, but I'll try to do my best to cover the material in enough depth so that it's understandable to all. So here's an outline of my talk today. First of all, I'll give some motivation for 6G. Then I'm going to talk some about performance metrics and application scenarios that we might expect for 6G. I'll mention some of the enabling technologies. This is where I'm on a little more firm ground, because this is where I do most of my research. I'll talk about some of the new paradigm shifts we can expect to see in 6G. And then I'll wrap up very briefly with summary. And then if we have time at the end, I'll be happy to take questions. So let's start with a little motivation. So first of all, what do we have in 5G? So 5G, as I said, is really just now rolling out. So there's some major things beyond 4G that we get for 5G. One is enhanced mobile broadband. Data rates up to a gigabit per second. Massive machine type communication. So One of the big advances in 5G, of course, is the fact that many of the users, if you will, are not human beings, but rather they are machines. So the number of possible users grows dramatically when machines can be terminals on the wireless network. And then part of the enabling of machine type communications is the development of ultra reliable and low latency communications. I'll say a bit more about this going forward. So some of the key technologies that have been introduced for 5G, one is millimeter wave, of course. We moved from microwave. We've included, in addition to microwave, we've included millimeter wave communications, massive Mimo, that is massive numbers of antennas on base stations in order to get much higher throughputs, and ultra-dense networks, that is networks where we have many, many terminals in a small space. Now, so why do we need 6G? Well, even though 5G has achieved great advances, there are many requirements that we might look forward to in 2030 when 6G is going to be rolling out. So in addition to guaranteed latency, which is being provided by 5G, 6G is going to require high time and phase synchronization accuracy. And I'll talk a bit more about that later. Also, we're going to look to have 100% coverage everywhere on Earth and sub-centimeter geolocation accuracy. This is to support things like robotics and factory automation. And then there are going to be other applications, 3D video, virtual reality, augmented reality. These are going to require terabit per second level of transmission data rates, while 5G can only provide gigabits per second. Now here, you know, when I first got into this business, 30 years ago or more, the idea that you could support gigabits over wireless was like a pipe dream. But today we have gigabit per second wireless, and I'm confident that we will achieve terabit per second as well in the future. And then, of course, one of the big stories of wireless today is the fact that end user devices collect data, and there's a tremendous amount of data out there, many different scenarios and all kinds of services that can arise. And so 6G will be a time when artificial intelligence will really come into its own in wireless networks. So again, just continuing a bit on the same theme of why we need 6G. Well, you know, up to 5G, traffic has been dominated by video, right? That's really the big, where most of the traffic is. And in 6G, there'll be other applications. So network control of robotics, okay, for example. This is going to create new challenges. For example, you'll have many robots in a typical application. They have to share control information, and that's going to overburden centralized controls. So distributed control systems using AI are going to become a necessity in 6G. When it comes to machine type communications with robotic applications. So what are some of the performance indicators that we're going to look for in 6G? Well, as I already mentioned, peak data rates of a terabit per second. So, you know, another 3 orders of magnitude beyond 5G, which seems almost impossible, but I'm confident that we'll get there. Very high connection densities, 10 million devices per square kilometer. These are not people, these are things. Very tight latencies, less than 0.3 of a millisecond in order to control things very precisely. Energy efficiencies up to 100 times what we have now, and spectral efficiencies up to 10 times what we have now. Positioning accuracies will need to be very tight. Indoor positioning less than 10 centimeters, again, to support robotics and things of that sort. Outdoor positioning on the order of a meter. This is to support applications such as automated driving. So what are some of the applications we might expect in 6G? Well, first of all the things we're doing in 5G, we're not going to go away. I'm sure many applications will arise over 5G capabilities, but there are going to be also a lot of new scenarios. One is human-centric services. That is, services that are designed to take advantage of or to cater to what humans need, privacy, other things, rather than what the network needs, which is speed, bandwidth, and so forth. Industry 4.0 and robotics, I've mentioned that already a couple times. The increasing use of wireless networks in managing factories to increase efficiencies. I'll say a bit more about that as well. And then convergence of all the types of things that happen over a wireless network. Communications, of course, computing, I'll say more about that, control, localization, and sensing. So a whole host of types of systems, applications will need to take place over wireless networks, and they have to converge to do so. Space, air, ground, sea integrated networks. I'll discuss this again a bit later. This is to provide universal coverage. And then distributed AI, things like federated learning and things of that sort, where artificial intelligence is distributed out into the network in order to optimize it in various ways. And I'll talk a bit more about that as well. So just some examples. One is cloud virtual reality. So of course, I think you know that virtual reality is a simulated experience that can either be similar to the real world or completely different. It can be augmented in some way. One of the most important aspects of virtual reality is computing power. It takes a lot of computation to support virtual reality. And doing that over wireless link is a really big problem because latency, of course, because of human perception and so forth, is a big challenge of a cloud VR system. So this is a big challenge for bringing virtual reality to reality, if you will, over wireless, but this is one of the things where, in particular, terabit per second communication can be useful. Industry automation, I've mentioned it a few more times, but a few times already, but Industry 4.0 aims at enabling industrial production with improved flexibility, usability, and efficiency based on cyber physical system, which factories consist. So the physical system is the factory itself. And then on top of that is the cyber layer, controls, communications, sensing, and so forth. And Industry 4.0 wants to bring all that together to improve factory operations. So, for example, mobile robots, I mentioned before, remote maintenance, and plant asset management are some of the use cases that might come up here. Now, one of the challenges here is that factories, unlike wireless networks, factories have a very long shelf life. So, you know, when we think about enabling Industry 4.0, we need to do that in brownfield, that is, in existing factories. So that means that we have to, there's going to be a lot of requirements for seamless integration of cross-industry technologies in this field. So let me talk now about some enabling technologies that will help support all of these applications. And one is has to do with air interfaces and data transmission technologies. So one is multiple access. And now multiple access, or in general access techniques, really have been the key milestones to the evolution of cellular networks. If you look at the air interface, you know, first generation was FM, so analog FM, voice only. Second generation was TDMA, and it supported text. Third generation was CDMA, or a combination of CDMA and TDMA. So time division multiple access and code division multiple access, supporting web browsing online over wireless, okay? And then in 4G, we got to OFDM, which is where things have stayed for 5G. So orthogonal frequency division multiplexing. So 6G is going to require much higher spectral efficiencies and other efficiencies. And one of the potential multiple access techniques that might help define 6G is NOMA, non-orthogonal multiple access, which has been under study for a number of years now and is actually a part of 5G standards, but not widely used in 5G. But the idea is that NOMA can allow users to take advantage of dynamic channel conditions to get an increased spectral efficiency. I think we can expect to see more of this in 6G. Actually, the idea of NOMA goes back a number of years, back to multi-user detection, which is a key aspect of NOMA. But in earlier generations of wireless, signal processing technology, and by this I also mean semiconductor technology, hadn't really advanced far enough to allow for the practical implementation of something like NOMA. Today, we have that technology, and certainly in 10 years, that will go even further. So now non-orthogonal multiple access is something that can be reality. Another aspect of the air interface is spectrum sharing. Now, we've been talking about spectrum sharing for quite a while, cognitive radio, but this again is something where technology and processing power and so forth can now allow us to do these things. So this is going to be very important in order to deal with the issue of limited spectrum that we're going to have with very high terminal densities. So we can do this in the unlicensed band where we already have a lot of freedom in how we deal with technologies. So symbiotic radio, which goes beyond cognitive radio, is a recent evolution in spectrum sharing, which can enable massive access. And so symbiotic radio, unlike cognitive radio, symbiotic radio goes beyond and also allows terminals to share infrastructure and so forth. So again, we have very complex environments. We're going to, and AI again is going to be an effective enabler to support the management of the spectrum in this very complicated situations. So, another aspect, of course, of wireless with so many different terminals and so many different applications is going to be the need to transact in the wireless network. And one way to do that in a trustworthy manner is to use blockchain. Okay, so in particularly for IoT, Internet of Things applications, when you need some security, blockchain is a good way to provide that security. So you can run smart contracts, for example, enforce various actions such as authentication and control. Okay, and so then this allows us to create trusted physical links to support a number of services and support something like, for example, federated learning. Big challenge with blockchain is latency, because as you likely know, if you study blockchain, there's a very high latency with blockchain. So in any applications where latency is an issue, blockchain has to be improved. And of course, there is research in trying to reduce the latency of blockchain. It's a trade-off, though, between some of the security features and latency. So this is an issue with blockchain. Also, scalability is another big issue with blockchain because, as you know, it requires many miners to create a trustworthy environment. And the more users you have, the more that needs to scale up as well. So blockchain is a useful paradigm, but it needs a lot of research, a lot of advances before it can be used in some of these applications. Another aspect of emerging aspect of the air interface is cell-free Mimo. So multiple antenna systems where the multiple antennas are to spread over multiple cell sites. So of course, the classical wireless network has a cell which owns certain terminals within its cell, the cell site which owns certain terminals within its cells and services them. In a cell-free architecture, there are no cell boundaries during data downlink transmission, and every base station that can see a terminal can be part of providing a service to it. Okay, then in order for this to happen, you have to have cooperation among access points, and you have to overcome intercell interference. And again, here's a place where either pre-coding or multi-user detection can play a role. Some of the issues with self-re-MIMO are high implementation complexity. The more terminals you have, the more antennas you have, the more complicated the signaling environment you have, the higher the complexity. Also, there's a much higher load on backhaul and front haul. So you think about trying to coordinate all of these different cell sites or access points, and do that by uploading data into the cloud, doing the computations there. This is just going to create a greater burden on the front haul and the back haul. Okay, and of course, it all relies on getting accurate channel state information, synchronizing various access points and so forth. So there's a lot of challenges here. At this level, there are also a lot of other challenges, unmanned aerial, other potential technologies, UAVs or drones, in order to create hotspot coverage and so forth, reconfigurable intelligent surfaces to provide, to tune the radio environment and so forth. So there's a lot of exciting research going on in these areas, and some of it will find its way into 6G. Also, beyond the air interface, at the higher layers of the network, there are other aspects of new technology that will find their way into 6G. One is software-defined networking. So software-defined networks, of course, are able to provide flexibility in the higher layers by running on general-purpose hardware with software that can separate the control and data planes. So you can program the architecture, making it agile, cost-effective. You don't have to build new hardware every time you change the network structure. And it also allows you to upgrade on the fly. One of the key enablers of software-defined networking is network function virtualization, where you transform network functions into software, and then it runs on the top of general-purpose hardware, as I mentioned earlier. One of the pros of this is that this makes the network elastic and simplifies its management. Some of the negatives are there are still issues like mapping the physical to the virtual, how to integrate different functions and so forth. So this is a research area, but it's a very promising one for creating some of the things needed for 6G applications. Another aspect, emerging aspect for 6G is how we distribute computing throughout the network. So cloud computing, which is supported by cloud radio access networks, provides a lot of computing resources, all that you need really in the cloud. But data has to be uploaded from the network edge to the cloud. So this can cause high delay. So for some applications, this is fine, but for many applications, that delay is intolerable, okay? So some of the computing can be pushed forward toward the edge of the network to get lower latency. Fog computing looks at the use of multiple layers that interact with the cloud and the edge. And then there's edge computing, which is in standalone mode. That is, it doesn't use the cloud at all. It only does computations at the edge of the network. Okay, and this can work for many applications where data is already born at the edge. So computation can be done there too, taking advantage of the advanced computing power of edge devices. So, you know, this is there's no one answer to how this architecture will shape up in 6G. There's just more flexibility. Different applications can take advantage of different properties of these types of computing architectures. So now let me talk about some of the new paradigm shifts that we hope to see in 6G. So 4 I'm going to mention. One is space, air, ground, sea integrated networks, which I've mentioned briefly before. The idea here is to combine satellite communication, drone communication, traditional terrestrial communications, and maritime communications into one integrated network. I'll say more about this in a minute. Another type of integration is across spectra. So today we have, of course, most wireless takes place in microwave band, sub 6 gigahertz. In 5G, we now have millimeter wave on top of that. For 6G, we're looking to build on top of that, moving up to terahertz band, and also to look at free space optical, things like Li-Fi and so forth. I'll talk about this again in a minute. Intelligence endogenous networks, where we use machine learning for network control and machine learning for resource management. So again, distributing AI out into the network. And finally, security, okay? And I'll talk a bit more about this. I'm going to dig a little bit into one aspect of security at the end of the talk. But there are enormous security and privacy problems that arise in the new applications for 6G. And I'll say a little bit about some solutions as well. So space, air, ground, integrated networks. So the objective here is to provide truly ubiquitous wireless communication services globally, So the advantages here are with satellite communications, for example, we can get seamless wireless coverage everywhere. Of course, it has the disadvantages of latency and so forth. Drone communications can provide great flexibility, mobility, adaptive altitude, and so forth. The resources can go where they're needed on an adaptive basis. And then, of course, maritime communications, well, the oceans covered 70% of the Earth's surface. So maritime communications are very important if we're going to have ubiquitous coverage. Some of the issues that come up, well, how do you manage all of these different networks? They all have different characteristics, different quality of service characteristics, and so forth. So how to manage them all is a major issue. And then how do we route among all these different networks, particularly satellites and drones? Energy efficiency is huge, particularly for drone communication. Energy efficiency is a major issue. And then what are the protocols that we're going to use to transport data across these networks? Well, here's a place where software-defined networking can play a big role, because it can allow hybrid and hierarchical network control that it will allow us to flexibly use these kinds of networks together. Similarly, we will want in 6G to integrate across spectral bands. So the idea, of course, is we want to provide this ubiquitous high data rate coverage. And to do that, we're going to need to take advantage of all the spectrum we can get. So again, we know from 4G and previous that we get wide coverage at fairly low cost in the microwave bands. So that's the traditional cellular communications. In 5G, we've added millimeter wave, and with that we get wide bandwidth, high capacity, and we're able to look at much more densely packed terminals because of the narrow beams afforded by millimeter wave. Terahertz, which is just being considered now, gives even larger bandwidth, better security, easy tracking, and so forth, because again, very narrow beams and very short transmissions. Optical bands, of course, we're thinking about LEDs, using them to modulating LEDs for communication indoors, and it's easy to contain that kind of thing. So security is enhanced. It's much easier to control what's going on with optical signals. So some of the issues are channel modeling and measurement. We don't really know how the channels look, particularly at terahertz. If we're going to integrate it and optimize spectrum use, we need to have metrics for how to evaluate spectrum usage. I mean, to do optimization, you need some kind of utility function. And then just how do we manage all these resources, okay? And now here's a place, again, where machine learning can play a big role, because the problem is just too complicated to think about optimizing in a more traditional way using analytical optimization. So, so this is, I think, where we're going to see another application of machine learning in 6G. Endogenous networks. Again, the idea is to enable 6G networks to incorporate intelligence and self-evolution capabilities. So one of the examples is, of course, two examples, of course, are the integrated spectrum integration and different network integration that I just talked about. So some of the advantages of adding intelligence is that we can use it to analyze what's going on in real time. What users are there, what quality of service do they need, and what are the environments that we have, what is the radio environment that we have to service those users. In order to realize things like stereo perception, which is a very non-traditional kind of optimization problem, artificial intelligence can play a big role there. Of course, decision-making problems like resource allocation in the factories and so forth. These are places where AI can be very useful, and just dynamically adjusting the network. So if you think about the air, sea, land network, dynamically adjusting where the traffic is, where it's going, depending on the environment and where the terminals are located, is something that can be done using intelligent networking. So there are a lot of issues. I mean, just thinking about creating a knowledge graph for a very complex network is a difficult problem. And how do we design the mechanisms that we want to use in order for networks to evolve? So there's a lot of work to be done here, but I think it'll pay off with a lot of efficiencies and doing things that we couldn't do without AI. Another big issue is security. Okay, and I'll just start out with AI itself. So there are a lot of security and privacy problems raised by AI. One of them is privacy. The data is often has personal data in it, the data that's used in training. And that data can leak through AI algorithms. So it's widely known that the privacy of data is compromised by machine learning. And also there's vulnerabilities in AI software that can be exploited by malevolent actors. So these are issues that have to be dealt with. And IoT devices themselves are problematic. So first of all, when you have a massive number of them, they can't necessarily all be authenticated. And so you might have malevolent or malicious devices participating in machine learning or other activities of the network. And due to the limited nature of IoT devices, these are not cell phones, these are sensors, actuators, and other lower complexity devices. They don't have the capability to support complex cryptographic algorithms like a cell phone could or a laptop. So some potential solutions, first of all, taking traditional cryptographic methods and replacing them with much more lightweight versions of themselves. So this provides lighter security. Another is efficient physical layer methods. Okay, and I'm going to talk a little bit more about that in just a second. And then finally, quantum-based methods where quantum technologies are being developed in parallel with the evolution of wireless networks. And so perhaps there'll be some quantum-based methods that we can take advantage of in the future. And then finally, I already mentioned blockchain, which is a way of enabling trust. Of course, it has its disadvantages as well, but again, research may overcome some of those disadvantages. So I think what I want to do now is to dig a little bit more into physical layer methods. I'll just go at a very high level, talk about that a bit more, and then I'll wrap up, and then I'll be happy to take questions if we have time. I see there's a number of them in the chat and in the Q&A. Okay, so let me just say a little bit about physical layer security and motivate it. Today, security is really implemented at higher layers of the network, typically at the application layer or the transport layer. And in current networks, it works well. That is, I think we can be confident that our cell phone or our laptop is pretty secure, at least in terms of the data communication capabilities. And we're completely comfortable using it, for example, for banking or other secure activities. So why would we need physical layer security? That's really a question. Why don't we just stick with what we've got? Well, a couple things I already mentioned, but let me just mention some of the good things about what we have today. First of all, there are no known feasible attacks. With a long enough key, your information technology is secure with cryptographic methods, okay? It's widely employed and tested. There's trustworthy authentication and so forth. Now, some negatives of standard crypto are that they're really built on unproven assumptions of the difficulty of computational problems, right? And so with the emergence of quantum computing, those assumptions may not hold true. Also, they're very computationally intensive in general. So as I mentioned already, IoT devices, for example, may not be able to implement standard crypto. And they require infrastructure, okay? So in some applications, the terminals are highly distributed with very light infrastructure, grant-free type access and so forth. So it may not be possible to manage crypto in some emerging network applications. Now, physical layer security is based on fundamental radio characteristics, that is, physical characteristics of the radio channel, which can't be beat by computation. Okay, so it's secured against quantum computations even. You can use the properties of the radio channel to generate key on the fly, so you don't really need infrastructure to generate or to manage key. And it's generally fast and lightweight. That is, the kind of encoding that you need for physical layer security is very similar to error control coding. So you don't need high complexity, or at least complexity beyond that kind of error control coding for physical layer security. Now, there are some disadvantages. First of all, a lot of physical layer security techniques rely on some knowledge of the eavesdropper, of potential eavesdroppers, and what their channels look like and so forth. So these are areas where there are workarounds, but still a lot of work needs to be done to make this practical. A lot of the theory, like a lot of other information theoretic principles, is based on asymptotic theory, whereas most of the applications where this would be interesting is for low latency, ultra reliable low latency type applications where the block lengths are going to be short. Okay, so that means we need to work on physical layer security, which is based on information theoretic security. We need to work on these problems for short block length, non-asymptotic problems. There is work along those lines, but a lot more needs to be done. And then finally, unlike standard crypto, this is really not reality today. This is still in its infancy. It hasn't been proven in applications. And so a lot more needs to be done to make it work. So prime example, though, where we need this is in something like the Internet of Things, because the number of devices, the infrastructure, the lightness of the infrastructure, the low complexityness of the devices, and the short messaging and so forth, all the things about IoT are things that sort of work against standard crypto. So physical layer security is a way of securing something, securing Internet of Things type applications. Now, one thing to think about is that the level of security needed for IoT may not be the same as the level of security you need, for example, for banking or for some other very highly secure applications, right? So you can think about physical layer security as a way of providing best effort security in certain situations. So you can think about, like we think about quality of service in wireless, we could also think about quality of security as a parameter. And one extreme is, very high power crypto, And another extreme is physical layer security. And somewhere in between, we might do combinations. One might augment the other. So we have to start thinking about security as being something that's not necessarily bulletproof, but rather something that we do to the best of our ability, just like we provide quality of service to the best of our ability. So here's an example of what might go wrong if we don't secure our IoT networks. And this comes from a paper a couple of years ago from USNICS, which is a security conference in computer science community. And here we looked at an IoT application, namely smart grid, where IoT devices are used to control high wattage devices throughout people's homes, so air conditioners, refrigerators, and so forth. So if in the U.S. and I think probably in Singapore, we have Nest, which is basically an IoT application to control household appliances, okay, over the internet. So what we looked at here was what would happen if botnet of the size of the Mirai botnet, which was a real botnet that got out a couple of years ago, and control 600,000 bots. If we could control that many water heaters that were on, say, using Nest, and turn them on or off instantaneously, and simultaneously, that would be like controlling a 3 gigawatt reactor, which is, it would be like switching on and off the largest currently deployed nuclear plant. This would be highly disruptive to the grid. I think anyone who is familiar with the electric grid knows that it has to be kept stable, and sudden load, either up or down, can be very disruptive and can cause load tripping, generator tripping. It can cause cascading failures and so forth. So this is a real threat. IoT devices are not very secure today. I think we're fortunate that there really aren't that many of them yet, but someday there will be, and when they are, they'll be vulnerable. So we really need to start thinking about these things now. So what about physical layer security? Well, I mentioned, it can really offer best effort security. I think that's the way to think about it. There's a lot of things physically about wireless that cannot be attacked this way. And there's my ding, I think. So let me just wrap up quickly. So we have, in message integrity, we can look at things like the fingerprints of wireless devices, physically unclonable functions, and so forth. We can look at biometrics, other things of that sort. And for message confidentiality, we can look at wiretap channel coding, so wiretap codes, and secret key generation, as I mentioned before. All right, well, since I've heard the signal, I'm gonna just wrap up. This is my last slide. So what have I talked about today? Well, I talked about some ideas about 6G, some of the metrics and applications. Global coverage is one of the things we want. Enhanced spectral energy, cost efficiency, better intelligence level. Some of the enabling technologies, we talked about air interfaces and transmission technologies, network architecture, things like software-defined networking. And then I talked about these paradigm shifts, space, air, ground, sea integrated networks, all spectra integrated networks, intelligence, endogenous networks, and some security issues and solutions. And I took a little bit of a deeper dive into physical layer security. So with that, I'll thank you. And I'm gonna now, it looks like I have about 15 minutes. I won't take it all, but I'll start looking at the questions and see what we've got here. Okay. Let me just give me a second here, get back to myself.
Thank you so much, Professor Vincent Poor, for that presentation. And I'll be joining you for this Q&A segment. We've got quite a number of questions for you. Lots of members of our audience are truly interested to find out some of the more about what you have presented. We're going to start with this question from a person called PG Patil. And PG Patil would like to ask, how will 6G help in the privacy of MFG, I believe that's manufacturing plants, and ensure information security? Which is the greatest challenge implementing digital ideas in MFG? I'm assuming that's manufacturing, especially in pharma companies. What's your take on this, Prof?
Yes, well, very good question. Some of the things I mentioned already, I think, will come into play. I mean, for example, if we think about using AI out at the edges of the network, one of the big issues, of course, is the privacy of that data. And one of the potential ways of protecting privacy is to use something like differential privacy in order to hide sensitive data. But that's not enough. We also have to worry about things like poisoning attacks on machine learning algorithms and so forth. And there are ways of defending against those, but certainly they're going to have to be built in to wireless networks before they can be used in a trustworthy fashion in manufacturing or other cyber physical systems. So it's an excellent question. I think there's a lot of research to be done, and I think it has to be done before we can really trust these systems. So.
Thank you so much for that answer. We have another question for you. This time it's from Shemuel Yerushalmi. And the question is, according to your opinion, how do 6G technologies help in preventing social and economic crises? Among others, can 6G help in predicting financial frauds, for example?
Well, I mean, I think. Let me just say that there's probably, if you think of 6G as a technology, it may not in itself be able to address that problem, but it may create infrastructure that allows, say, bank examiners or others to gather the data that they need in order to look for, for fraud and so forth. But I think actually fraud detection is probably something that's it's an application would have to be done maybe using data gathered by 6G network, but not necessarily using anything particular property of 6G. It's an interesting question. I think social, you mentioned also social issues. Right. I think, the distribution of, terminals with all kinds of capabilities throughout society can certainly address social issues, right? I mean, I mentioned the power grid, making it more efficient. Of course, a big issue is climate change, and making the grid more efficient is certainly a way to address that issue. And I think 6G can have a role there by allowing the deployment of sensors, actuators, and all kinds of other technologies that allow much greater efficiencies in the energy grid. So, that's one example. Hospitalization is another one. Of course, healthcare is a big social issue. And I think 6G, with some of the human-centric applications that it can support, sensing and so forth, I think can go a way toward improving healthcare. And also senior, the well-being of seniors in our society. I think having 6G technologies, various kinds of IoT, can allow seniors to live in their homes longer and be safer. So I think there are a lot of social issues that can be supported by 6G capabilities. How they're supported, I think, will involve not just people like us, but will also involve social scientists and medical professionals and so forth. So.
Thank you so much. Some really good examples there. Thank you so much for expounding on that question. And we still have some more questions pouring in. This next one is from Neil Kundu. And the question is, how can the spectrum efficiency be increased 10 times? Will it require a completely new modulation and coding scheme? What do you think?
Well, I mean, one way of increasing the spectral efficiency I mentioned already, which is NOMA, non-orthogonal multiple access. So sharing the resources among multiple users. So that may not get us to 10x, but it could get us to 2 or 3x. Okay. And then to get the remaining, we have to look for other efficiencies, better coding. Certainly, if we can do security using more lightweight security, then we need less spectrum to deal with encryption and so forth. So I think all of these things can add up to spectral efficiencies. And then another aspect too is, looking at, just not only spectral efficiency, but using more spectrum, which I've already mentioned. That's not necessarily an issue of spectral efficiency, but it is a way of dealing with the fact that we just don't have enough spectrum to support this kind of activity. So terahertz, optical, so forth, these kind of things can also be part of getting the spectral resources we need.
Thank you so much, and we hope that answered that particular question from our audience. Next question is, with 5G, 6G, and beyond, will there be a tremendously increasing demand for data storage and security? What are the potential challenges in this area? What do you think?
Well, I already spoke a little bit to a couple of the challenges. I mean, one is, of course, privacy. That's a tremendous issue. Security of data is another one. Just securing data. We see even the most sophisticated corporations and organizations have trouble protecting themselves from cyber crime. So this is just going to multiply as we have more and more data. I think there's a lot of work needs to be done in order to make all of our cyber systems more secure. And this is certainly an aspect of it. As our lives become more data intensive, our healthcare data, if it's all, in the US, healthcare data is primarily on paper. I know in some parts of the world, it's mostly now electronic. But as data like that becomes more electronic, it becomes more vulnerable. And I think, data about other aspects of our lives, not just our health, but our lives in general. There are a lot of private things that people that need to be protected, religious things and so forth. And the more and more data there is about us, the more we're going to have to worry about that. And I think the technologies is part of it. It's probably the biggest part of it is technology. I think that I would say that. Unlike some of the other things we discussed, this is really where technology is at the core.
Great. So there's some more questions for you. This next one is about dynamic spectrum. It says, for dynamic spectrum from sub 6 gigahertz all the way to terahertz, what is the implication on the hardware at the UE and base station?
Okay, so the UE, of course, the UE being user equipment, meaning the end user device. It has to be capable in multiple spectral bands. Now, not every device has to be capable for every band. I mean, your phone, for example, can still be a microwave phone. But for IoT, when you have very densely packed networks, you might want to have the capability of using some radio and some optical communications and so forth on the same device. And in fact, I think just in terms of, for example, your laptop could easily have, multispectral capability. One of the spectral being LED communication, and another one being microwave or millimeter wave or so forth. So I think, we're going to have to deploy multiple spectral bands on individual end user devices. Now, the infrastructure, that is the access points and base stations, I think is the term that was used, they're much more sophisticated devices. So, they can have multiple radios on them, of course. And I don't know that the same access point would really be necessarily multispectral. You might have small access points, which are terahertz access points, slightly larger coverage area for millimeter wave and then traditional microwave cell sites. So I don't know how it'll work. Certainly the end users have to be able to respond to whatever spectrum is available. You know, the infrastructure can be a little more partitioned. We'll just have to see how that works out.
Great. We still have a bit more time, and another question from Zi Wei Chua. And the question is, what are the time signal accuracy requirements for time synchronization and reference? Time signal dissemination accuracy needs to meet the 6G network's low latency or time stamping requirements.
Yeah, so you know, I think these are still being worked through. I mean, we have you know, another decade of research to work on these kind of things. But you know, I mentioned already, you know, 3.3 millisecond latencies, for example, and you know, sub-mil and sort of 10 centimeter type of localization accuracies. Okay, so these kind of accuracies assume very tight synchronization, right? You just can't get them without that. So I don't know exactly how to translate that into synchronization, but I think the end application is really based on things like positioning accuracy and latencies, and so those requirements are going to drive the requirements for synchronization accuracy and so forth. I mean, an example for if you look at cell-free architectures, right? I mean, in order for that to be useful, if you're transmitting at terabits per second, the signals have to arrive from multiple base stations in sync. And if the data is going at terabits, that tells you right there that you've got to have very, very sharp timing accuracy in order to get that kind of synchronization. So it's going to be another multiple orders of magnitude improvement in what we have today. I think maybe that's a good way to phrase it.
Great answer. And we have time for just one last question. This will be the last question, and this one is about health concerns, and it's from Wahajat Nasa. And the question is, what may be the effects of 6G on human health? What would you say that could be?
Well, I think I already addressed that. I mean, I think, you know, one of the great capabilities of even 5G and going forward into 6G is, you know, health, body area networking, where you can monitor what's going on in your body, you know, in real time, and it can be, you know, downloaded to your cell phone for analysis and so forth, or it can be transmitted to your physician for analysis. So people with, for example, heart conditions, you know, rather than being monitored once a month, they can be monitored in real time, and, you know, data analytics can be used to let them know if there's some issue that they need to deal with, and that's the capability you can only get with a body area network. There's really no other way to do that. And then the other one, so I think that's, you know, for certain diseases, I think it's a game changer, really, in terms of management and the kind of lifestyle people can lead when they do have those diseases. You know, I think diabetes is another one, right? If you have the right sensing, you can keep track of that in real time. You know, I think the other thing I mentioned was, you know, aging in place. I think that's a big trend. I don't know in Singapore, but in the US, certainly that's a big trend for seniors to stay in their homes much longer. It's much less expensive than, you know, being in a nursing home, and it's also much nicer. And I think that can take, you know, I think, you know, again, there's a, you know, with IoT devices that can detect falls or things of that sort, or other issues that seniors may have. I think that's just a way of prolonging the quality of life of people well into their senior years. So I think that, it's going to have a lot of impact. It won't all be 6G. I think some of it will be 5G. I think it's already, some of these capabilities are out there, and it's just a matter of developing the applications on the infrastructure we have. Some of the ultra low latency might be helpful in something like robotic surgery, for example. So that's another sort of whole nother area of healthcare where I think there we might find it even in 5G. So.
Thank you so much, Professor Poor, for taking the time to answer all those questions from our audience. And of course, thank you, the audience as well, for submitting all those questions. And we look forward to even more participation in our later sessions. Thanks once again to Professor Poor for that inspiring talk as well on 6G wireless communications network. Thank you so much.
Thank you all. Thank you all. Enjoy the day. It's bedtime here, so good night.
Good night. Good night.